right, so last period I discovered that people didn't know what weed eaters are. So those of you that haven't had to do yard work with your parents may not know what a weed eater is. It's that little device, it's a long stick at the end of it. There's this little string wire that hangs out. It's usually bright orange or some bright color. It spins around rapidly, and if you put it near a weed, it cuts it off. Yes.
For this one, it seems like if it costs 2 hours more of labor to get only $10 more of profit, it would just be all electric models.
Okay, so that's your theory. You think all electric. Let's see if that's true. Okay? Well, let's see. Let's see if that will give us the optimal solution. Okay? So I like you thinking like that. What do I think it will be? All right. Now, these are the steps that we're going to follow to do a linear programming problem. So in these, we will just have two variables. In the real world, we might have more than two variables. But this type of method will work. Now, I'm going to go ahead and label mine X and Y because for me, X makes sense down here, Y makes sense up here. But you certainly could label them G and E for gas and electric. Okay? Now, when you're reading this last sentence here, the question always tells you what your variables are. This question says, how many of each type of weed eater should the company produce? That's my question. So it tells me my variables are the types of weed eaters. And the two types that I have are a gas model and an electric model. Alright, so our first step is to label our variables. And you don't have to call them X and Y, but if you do, also label your axis that way. Now, the second thing we're going to do is list all of our constraints. In this scenario, what were our constraints? Now, two constraints that we always have to keep in mind, if we look back over here at our babysitting problem, did you guys notice these two constraints? X has to be greater than or equal to 0 and Y has to be greater than or equal to 0? Because is it possible for me to babysit or garden a negative number of hours? No. So when we're reading these problems, we always have to keep in mind that too. Is it possible to manufacture a negative number of either model? So I know X has to be greater than or equal to 0, and I know Y has to be greater than or equal to 0. And that's nice because now I'm just dealing with this first quadrant. So this entire graph could represent quadrant 1. Yes, ma'am? Oh, okay. I'm going to work through this one and then you could help me out with the next one, okay? Alright, when we're reading through, when we're looking for our constraints, we're looking for limitations. And if we read the second sentence, it says the gas weed eater requires 4 hours of labor and the electric requires 2 hours of labor, and the company has at most 800 hours to use in manufacturing each day. Okay, so Rose, what was the inequality you deemed from that?
It's like not really inequality, just like a statement that it has to take at least 4 hours to make one.
Okay, 4 hours for each gas. And how much for each electric? 2 hours for each electric. And it says we have at most 800 hours. Less than or equal to. Good, less than or equal to 800. Now some of you are going, Miss Willoughby's lost it because there are only 24 hours in the day. And she has us doing 800. Where do you think this 800 hours might come from? People hours. Yeah, we could have 100 employees. And if each employee worked 8 hours, how many work hours is that? 800 work hours. Okay? So that's where that's coming from. Okay, are there any other constraints or limitations that we could represent as an inequality? Okay, you see? All right, so the next sentence, the combined total of each type that can be manufactured is at most 300. What do you think that combined total? Very good. X plus Y is less than or equal to 300. All right. we do have a few more numbers. So let's see if those are constraints. The profit on the gas model is $50, and on the electric model is $40. Is that a limitation or constraint? No. That takes us back to something we talked about yesterday. We talked about an objective function. What is the objective of this problem? What do we want to do? Maximize profit. So for us, our objective function involves maximizing the profit. So we would write an equation to represent that function. For profit, our profit can be found how? Okay, Colin?
Is the how many gas ones you make and how many electric ones you make?
Uh-huh.
So I'd be 50x plus x.
Yeah,
50x plus 40y.
Plus 40y. Perfect.
It's not all electric. I think.
Okay. So have we used up every single number in the problem? Have we addressed every limitation? Yes. So once we've done that, then what we're going to do is we're going to graph our constraints. All right, so I'm going to go ahead and label this. What is this graph going to represent? The types of weed eaters produced. I'm going to label my graph, types of weed eaters. And then I let the x-axis represent the gas model, and I let the y-axis represent the electric model. And now I have to graph. But I'm not going to start graphing blindly. I need to determine what kind of scale to use on my axis. What do I want to count by? And the easiest way for me to do that is to find the x and y intercepts. Because that'll give me the largest x and the largest y I need. Okay? So if I plug in 0 for x into this first equation, I'm left with 2y equals 800. So what would y be? 400. And if I plug in 0 for y, I get 4x equals 800. So what would x be? 200. And then I do the same thing for the second equation. So I'd plug in 0 for x, and what do I get out for y? 300. I plug in 0 for y, and what do I get out for x? 300. So it appears my greatest y is 400, and the largest x is 300. So what is a nice counting number that might get us to 300 and 400? 20. Let's try 20. I like it. 20, 40, 60, 80, 100. 20, 40, 60, 80, 200. 20, 40, 60, 80, 300. Okay, let's try it on the vertical axis and see if we make it. 20, 40, 60, 80, 100. 20, 40, 60, 80, 200. 20, 40, 60, 80, 300. Oops, gonna be close. 20, 40, 60, 80.
Yeah.
Nailed it. Nailed it. Perfect. 400 is that top one.
But the bottom, the x doesn't get to 400.
And it doesn't need to. The largest x I had was 300. That's why I stopped at 300. Okay? Now, if we didn't make it far enough, we might want to count by 25s or by 50. Just pick a nice counting number.
Or you just make the graph big.
Okay, so go ahead and graph these using your intercepts. And having an accurate graph is essential to getting these problems right. So if you don't have a straight edge, you probably want to borrow one. Wow, that was really big.
Teach them. You don't got to take. Or you better tomorrow. Let's try the end.
Okay, go ahead and graph and share. Graph and shade your overlapping region. Accuracy is critical.
Ooh, that accuracy.
Instead of shading, can we just do the lines?
Yeah, just do a little bit. Okay, when you are done shading, look up and see if it matches mine.
What's that white one?
It's because I want to write something. Okay, so hopefully you got the same overlapping shaded region as I did. And in a linear programming problem, we call this the feasible region. Because any point that lies in this region, and because it's greater than or equal to, it's the dark blue also. Any point that lies in that region is a feasible solution to this problem. It will work, but it may not be the optimal solution. The optimal solution always occurs at a corner point or a vertice of our feasible region. The optimal solution will be one of the points that form this polygon that represents my feasible region. So test vertices could also be called corner points because they're the corners of that feasible region. And one of these test vertices, or corner points, will maximize our profit.
Nothing in here will, but one of these will.
Right.
Always over.
Now all of these will work. All of these will satisfy these conditions. But only one of these test vertices will also maximize your profit. Okay? So, we have the point 0, 0. We have the point 200, 0. We have the point 0, 300. And we have the point, what's that final point? 100, 200? 100, 200. Okay, now, where would we test these vertices? Where would we plug them in? What do you think, Luke? Into our profit equation.
Oh,
So, yeah, all of these get plugged in here, and whichever one produces the most profit is our optimal solution. So if we plug in 0, 0, obviously, if we make nothing, we also make no profit. If we do not produce any weed eaters, we make no money. Okay, but if we produce 200 of the gas model, by plugging 200, do you notice that I would make $10,000? Not bad. Okay, but if I produce 300 of the electric models, now I'm up to $12,000. Because 300 times 40 is 12,000. Now, what would be the profit if I produced 100 gas and 200 electric? Plug it in. You guys plug it in and you figure out what the profit would be.
13. So, yeah, 13,000.
13,000. Good. So if we produce 100 gas and 200 electric models, we would have a profit of 13,000. Well, guys, this is the optimal solution, isn't it? Because we wanted to maximize our profit. So our solution would read, the company should produce 100 gas models and 200 electric models for a profit of $13,000. Now, we have made some assumptions. We're assuming that we will sell everything we produce, aren't we? So, there are assumptions that have been made in this problem. Now, were you right?
No, but I said but if the workers are paid over $10, you could fire off the excess workers, and then you would get the maximum profit from the 0 to 300. If you fired off the excess workers, but assuming they made more than $10. But
What's much more?
it works. It works.
Firing people.
If they can make
Why
it,
would
if
you
they
fire
can make it,
your
if they can make it, I don't know, 300.
All right. Now the two on the back are your homework. I want you to get started on number 1. Get started on number 1, and I'm going to go over the constraints with you in just a minute.
Yeah, it would. Gotta think of all the time.
Okay. I was just asking a good question. The question was, does a maximum always occur where the two lines intersect? Well, if we only have 2 lines, yes. But this number 1 on the back will have 3 lines. Okay? We could have 4, 5, 6. Yes?
Is the one that maximizes profit closest to the dead middle of the graph?